Okay, we are going to begin uh, chapter 2, which is called Motion in One Direction. And let's share the PowerPoint and begin. Now, this is motion in one dimension. Is going to give you some basics about position, speed, velocity, and acceleration. And it's going to be expanded to 2 dimensions and eventually 3 dimensions. And it's very important. This is a very important section. It gives you fundamentals about calculating position, velocity, and acceleration, which will be key throughout the remainder of your studies. Even next semester, I'm teaching 24-26 this semester, and they're going to be using some of these same equations. So this is fundamental, and this is something to study well and know it well. Okay, let's take a car. You can see that at A, at time 0, if you look at the chart, it's a table, the different positions A through F, and you can see that it's timed every 10 seconds, 0, 10, 20, 30, 40, 50, and it gives you the position. So at time 0, the car starts at 30 meters. Then at B, it goes to 52. Then it reverses at C. It's at 38. At D, it's at 0, the origin. And then at 40, it's minus 37. And at 50, it's minus 53. So the car moves in one direction and then reverses back in the other direction. And you can see the plot. That's a position, X on the vertical axis, and time on the horizontal axis. So it starts at 30, goes to 52, and you can just follow the graph: 38, 0, minus 37, and minus 53. So it's represented 3 different ways: just pictorially, a table view, and the graphical view. And that's what we have here: pictorial representation, a tabular representation, and a graphical representation. We'll use probably the table and the graph the most in the remaining chapter. Okay, so the displacement delta x of a particle is the change in position in a given time interval. So delta x is equal to x final minus x initial. We're going to use that f and I often. We're going to have initial velocity and final velocity, initial acceleration and final acceleration. And usually when we're talking about a delta x, delta v for velocity, or delta a for acceleration, we have you do the final minus the initial. So the displacement delta x is x final minus x initial. So if you what is the delta x from A to B? Well, the final position is at 52 meters, and the initial position is 30. So the delta x for that interval would be 22. So that's displacement. It's a difference in position. Now, if you talk about, there's a difference between distance run, and you can see here the basketball players. They're going to be running all throughout the game, but their overall displacement is going to be near 0. Another way to think of it is somebody running a 4-meter race. They start off, especially if they're on the inside lane, they start off at a starting point, go completely around the loop, and cross the finish line basically where they started. Now, the distance they've run is 400 meters. Their displacement, as soon as they cross the finish line, is 0, because they are back in the same place that they started. So the displacement from their initial position and their final position is 0. That may take some getting used to, but I think you will get used to it after a while. So there's a difference between distance and displacement. So a vector we have two quantities. The distance traveled is a scalar quantity. It has numerical value and no direction. So if somebody runs a 400-meter race around a loop, it doesn't matter what direction they're traveling. We just know that their distance, they've traveled 400 meters. Whereas a vector quantity requires a specification of both direction and magnitude. So when I make I live over here at the medical center, and so when I travel to St. Philip's, my general direction is a southeasterly direction, but there are times when I'm going due south, there's times I'm going due east, and there's probably a few times when I'm on city streets just to get to the highway that I want to get to, I'm actually traveling north, but the overall distance is southeast. So the vector quantity, my vector changes throughout the my travel, but my overall scalar quantity, I travel about 17 miles to get from home to St. Philip's. There's a difference between distance and displacement. The displacement usually is a vector quantity that shows a distance and a direction. Okay, so we look at this. Let me see where we've discussed this already. The position, the speed, and the velocity and speed of a particle. The velocity and speed we use interchangeably, but the velocity has a vector connotation. It's a speed in a particular direction, whereas speed, it doesn't care. It doesn't matter what direction you're going. It's just a quantity. It's a scalar quantity. So velocity is a vector quantity, and speed is a scalar quantity. Let's see the notes. I don't think when I say notes, I'm just looking at the book. Okay, let's go on. Which of the following choices best describes what can be determined exactly from the table and figure for the entire 50-second interval? The distance the car moved, the displacement of the car, both A and B, or neither A and B. Well, I'd say that if you look at the table and you look at the figure, you can look at the overall distance the car has traveled, and you can also see the displacement from its initial position. So I would say both A and B. And I'm wrong. Only the displacement of the car. So only the displacement of the car can be determined. So let's look at position, velocity, and speed of a particle. You can see that they have two quantities from A to B. They have a delta x and they have a delta t. Well, from that we can determine that the average velocity is the change in x over the change in t, and we get that it's basically a slope. You're looking at a slope from A to B, so it's the just like a slope. You have y1 minus y2 over x1 minus x2. You can get the slope here, and that gives you the average velocity over that period. Okay, so example, 52 meters minus 30 meters, that's 22, and it's a 10-second interval, so it's 22 divided by 10, and it's 2.2 meters per second that it's traveled. Okay, now the average speed of a particle is a scalar quantity, the total distance traveled by the elapsed time. So the average velocity here is the distance divided by the time. So in this case, we're talking about our average velocity. In this case, we're talking about average speed. So it's the total distance. It's not the displacement. This particular one, delta x, that's a displacement, and here it's talking about the distance traveled. Average speed is the distance traveled, and that's a scalar quantity. Okay, as an example, if you 75 meters divided by 55 seconds is 1.36 meters per second. Okay, and the average speed in this case is 125 meters divided by 55 seconds, and that's 2.27 meters per second. Do they have an accompanying? No, I don't see it. Okay, so there can be difference between the velocity and speed. Okay, under which of the following conditions is the magnitude of the average velocity of a particle moving in one dimension smaller than the average speed over the time interval? A particle moves in the x direction without reversing. A particle moves in the minus x direction without reversing. A particle moves in the x direction and then reverses the direction of its motion. And there are no conditions for which this is true. Let's read the question again. Under which of the following conditions is the magnitude of the average velocity of a particle moving in one dimension smaller than the average speed over the time interval? Well, if it just moves in one direction, either the positive or the negative, the average speed and the average velocity should be the same. But if it moves in one direction and then reverses, it's possible that the velocity would be smaller than the speed. So the answer is C. A particle moves in the x direction and then reverses in the direction of its motion. Okay. And that is it for the first section. We'll continue with instantaneous velocity and speed, and this is where we're going to get into a little bit of calculus. So you may be taking calculus concurrently, or you may have already had it. Either way, we'll get through this.